Welcome back everyone. In this lecture we will actually continue with the basic properties of symmetric groups. So in the last lecture we saw that given any permutation can be written as product of disjoint cycles. So now we will use that result and then prove that any permutation can be written as product of transpositions. So not necessarily distinct transpositions. So let me just state the result. Okay, here is the theorem. So this is somewhat very important result in order to understand given permutation. So you take any permutation sigma in Sn. Okay. So it is a product of transpositions. So they are not necessarily distinct. Okay. Disjoint. So note that if they are actually necessarily disjoint, then what will happen? If you write sigma as product of transpositions which are necessarily disjoint, so then that sigma must be involution. That means it must have order 2. Okay. But here we are talking about any given permutation. So now let us see how one can prove that. So this is just a corollary of what we have proved earlier. So given permutation, you can write it as product of disjoint cycles. Okay. Now if you are able to write given a cycle as a product of transpositions, then we are done. So we will do that. So you start with the cycle. Let's call it A1 etc. AK. So cycle of length k. So then what we want to do, we want to write this as product of actually transpositions. So let us do one example, then it will become actually very clear what we are talking about. So let's take this cycle 135 inside S5. So then you can see that if you actually arrange it, so first you take 1 5 and then take 1 3. If you take the product of these two, then you get 135. So let's see how it is done. So what is 1 5? So let's write it in terms of our permutation notation. So this is 1 2 3 4 5. So 1 5 is just permutes 1 and 5. So 1 goes to 5, 5 goes to 1, all other elements are fixed. And then you can see that 1 goes to 3 and then 3 goes to 1, all other elements are fixed. So now if you take for example 2, which is not from this support of 135, you can see that this 2 and 4. So they are fixed by both of these permutations. So in particularly 2 and 4, they are fixed in this product. Okay, no issue. So now if we take for example 1, then what will happen? So 1 goes to 3 and then 3 goes to 3. So that means, so in the product you can see that, so 1 2 3 4 5. So 2 goes to 2, 4 goes to 4 and 1 goes to 3, 3 goes to 3. So 1 goes to 3. Now what's about 3? So 3 goes to 1 and 1 goes to 5. So 3 goes to 5 and then 5 must go to 1. There is no other option. So which is same as 1 goes to 3. So let me write it here. 1 goes to 3, 3 goes to 5 and then 5 goes to 1, which is this cycle 135. Okay. So this is what we need to generalize. So this actually tells us what pattern it should be. So you take the first element, pair it with the last element and then you keep the first element and then pair it with the second last and so on. So then you will be able to get this cycle. So indeed you can write this as A1 AK and then A1 AK minus 1 and so on. So then A1 A3 and A1 A2. So, the product of these transpositions will be exactly equal to this cycle A1 etc. AK. For example, let us see where this image A1. So, the image A1 here on the left side should be A2. So, A1 goes to A2 on the left hand side. So, now look at the image on the right hand side. On the right hand side A1 goes to A2 here, but A2 is fixed here, A2 is fixed here in all these transpositions. So, that means A1 actually goes to A2 on the right hand side as well. Similarly, you can look at what happens to A2. A2 goes to A1, but A1 here goes to A3, but A3 will be fixed in the next transposition. So, that you can see that. So, A2 goes to A1 and A1 goes to A3. So, that means A2 goes to A3 on the right hand side, which is the case here. A2 goes to A3 here. Okay. Similarly, all other indices you can check what is happening. For example, if you take AK, so AK is fixed in all these k minus 1 transpositions. So, only AK will have effect from the first transposition. So, which actually sends AK to A1. So, that is the case here, AK goes to A1 here. So, that means the product of these transpositions is exactly equal to this given K cycle. So, now if you start with any permutation, that can be written as product of disjoint cycles. So, now each cycle can be written as product of transposition, but note that they are not necessarily disjoint, okay, because this A1 be there in common to all of them. Okay. So, in particularly given permutation can be written as product of transpositions. Okay. So, now here is somewhat special transpositions. Okay. So, transpositions, they are also very important. Okay. Transpositions look like this Ij, okay, where I and j both comes from. So, one can actually rewrite Ij is same as Ji. So, you can see that one can index this transposition as follows. So, where you write Ij, where I and j satisfies, they come from 1 to n such that I less than j. So, this is exactly the upper like strictly upper triangular part of the matrix. Okay. If you want to look at in terms of the matrices, so the diagonal will be here, which is II. So, if you take all these entries on the top, so that corresponds to exactly these transpositions. So, now how many are there? It is just exactly 1 plus 2 plus etc. n minus 1. So, this is exactly n into n minus 1 by 2. So, these many transpositions are there in Sn. Okay, the number of transpositions in Sn is equal to n into n minus 1 by 2. So, now if you think about, okay, so what this theorem says, as a group Sn is generated by transpositions. Okay. And if you actually look at how many transpositions are there, it is almost like n square. Okay. So, this is exactly like n square amount of transposition that are there, but that seems to be really lot for the group Sn. Okay. So, then we can ask, is there any smaller set of generators? Okay. So, one can actually prove that. So, there is this special set of transposition called adjacent transpositions or simple transpositions. Okay. So, I would actually like to call them simple transposition. So, that also will generate the group Sn. So, what is this? So, the simple transpositions or the adjacent transpositions, they are the transposition of the form I plus 1. So, basically you just switch only the ith index and I plus 1th index. So, that is this transposition does. Okay. So, this is a simple transposition corresponding to I. Of course, this can vary only from I to n minus 1. Okay, there are n minus 1 simple transposition. So, the claim is actually again the group Sn is generated by these simple transpositions I plus 1. Okay. So, how one can prove this? So, we already know that symmetric group is generated by all transpositions. So, it is enough to actually prove that given a transposition is actually product of the simple transposition. Okay. So, that is again somewhat easy. So, any given transposition looks like something like this. So, K L where K is less than L. So, this is how given transposition looks like. So, then one can check that this is exactly equal to the product of these simple transposition. You can take K plus 1 and then K plus 1 K plus 2 and then you go all the way up to L minus 1 L, and then what you need to do, you need to actually take the inverse of this, conjugate with that. So, that is exactly equal to, so L minus 2 L minus 1, okay, L minus 2 L minus 1 and then product up to K plus 1. Okay. So, this is what you need to take. So, if you take all these products, okay, then you can see that. So, this is going to be exactly equal to K L. Okay. So, let us do some example and then it will be like you can convince yourself that this is the case. Let us take S4 and then do this 1 and then let us say 4. So, then what this actually says, this is exactly 1 2 2 3 3 4, okay, and then you have to take now, okay, the L minus 2 is 2 and then 3 and then you go like one step down 1 and 2. Okay. So, the product of this is exactly 1 4. So, let us check this is the case. So, left hand side we understand very well, there is no issue. What about the right hand side? So, look at what happens to 1. So, 1 goes to 2 here, 2 goes to 3, 3 goes to 4, but 4 is fixed in this. So, that means if you write this as 1 to 4, so 1 goes to 4. Now, look at 2, 2 goes to 1, okay, here, and then 2 goes to 3 and then 3 goes to 4. Sorry, we wanted to look at 2 goes to 1. Yeah. So, what happens to 2? 2 goes to 1, 1 is fixed here and fixed here, and at the end 1 goes to 2. So, 2 goes to 2. Similarly, what's about 3? So, 3 is fixed here, but 3 goes to 2 here, and then 2 is fixed here, and then 2 goes to 3 here, and then 3 is fixed. That means 3 goes to 3. Similarly, you can see that 4 is fixed here, 4 is fixed here, 4 goes to 3, but 3 goes to 2 here and then 2 goes to 1. So, 4 goes to 1. So, that means this is exactly the cycle 1 4. Okay. And this is what happening here in this product as well. Okay. Let me just show by example. Let us see where K goes to. So, K here you can see that K goes to K plus 1. In the next term K plus 1 goes to K plus 2 and so on. So, then it will go to L minus 1 and then L minus goes to L, and L is fixed in all of them. So, that means K goes to L here. Similarly, if you take K plus 1 goes to K, but K is fixed in everything except the last one where K goes to K plus 1. So, that means K plus 1 goes to K plus 1. Similarly, if you go to K plus 2 here, what will be the term? This K plus 3, K plus 2. So, K plus 2 goes to K plus 3. It is fixed everywhere except in this term where K plus 2 goes to k plus 3. Okay. So, likewise you can convince yourself that all elements are mapped itself except L, because L is fixed in all these except here L goes to L minus 1. If you come down all the way, this L minus 1 goes to L minus 2 and so on, then finally that goes to k plus 1, which goes to k. So, then that cycle is completed, it gives you transposition KL. So, this is a simple formula that you can work it out by doing some examples. So, once the formula is given, you can easily see that this formula indeed works. Okay. So, this proves that this Sn is indeed generated by this simple transpositions I plus 1. There are n minus 1 transposition. So, there are again some more generating sets smaller than this. Okay. So, maybe I will actually add it in the assignments. So, but these set of generators, they are somewhat important from the reflection group point of view. Okay. So, as I said, this Sn has this another way of realizing. Okay. So, that is using this permutation of identity matrix. Okay. So, then this I plus 1 is indeed corresponds to switching this ith row and I plus 1th row, or jth column, sorry, ith column and I plus 1th column. So, whichever rows or column that you are actually permuting, depending upon that it will just switch. So, we will actually give that reflection group interpretation later once I introduce the isometries and reflection groups and so on. Okay. So, let us move on. As we actually noticed before, if you are interested in finding out whether given a permutation is actually having sign 1 or minus 1. Okay. So, we need to look at its cyclic decomposition and then see what happens. So, now we can also use this product of transposition and then see what happens. So, note that the cyclic decomposition is unique. Okay, because we are writing in terms of product of disjoint cycles, but this writing product of transposition, it is not something unique. Okay, one can write it in many different ways. But anyway, what is the advantage of writing it as product of transposition? If you write sigma as some product of, let us say, transpositions tau 1 etc. tau r, then you can see that the sign of sigma is going to be exactly minus 1 power r, where r is the number of transposition that are actually used here in this product. Okay. Why this is the case? Because if you take, for example, the simple transposition, okay, you can see that the sign of the simple transposition I plus 1 is going to be just minus 1, because just changes that ith row and I plus 1th row. So, what is about the sign of the transposition ij? So, that is also going to be minus 1, because it changes the ith row and jth row. Okay. But if you just work it out using this decomposition, okay, you can see that. So, exactly the same result that you get, because the sign is well defined group homomorphism from Sn to plus or minus 1. So, from that one can actually realize that if you write, okay, for example, okay, here is a result which is immediate once we know that the sign map is actually well defined group homomorphism from the symmetric group to plus or minus. If you write identity as product of some transpositions, product of some transpositions, so then this R must be congruent to 0 modulo 2. Why? Proof is simple. You just apply the sign map on both sides. The sign of identity is 1. So, that means this minus 1 power r must be 1. So, that will imply that r is congruent to 0 modulo 2. Okay. So, this indeed says it does not matter, okay, even though the product of transposition, if you write it sigma as product of transposition, that expression may not be unique, but still one can conclude that the number of transposition that is used in the expression, that must be either odd or even. Okay, that is what this simple observation tells. Okay, if you write sigma as product of this transpositions, you write sigma as some tau 1 etc. tau r and then some sigma 1 etc. sigma s, where tau I and sigma j, they are all transpositions. So, then we can conclude that this r must be congruent to s modulo 2. Either both r and s are even or they are odd. Okay, we cannot have mixed sign. So, in particularly we can have this following characterization: if sigma is in a n, if and only if sigma can be written as a product of even number of transpositions. So, this is one of the characterization of sigma being element of this A n. Okay. So, such sigma we call it even permutation, because the number of transpositions that are used to write sigma as product of those transpositions. So, that is always even. Okay. So, it does not matter which way we write, still the number of transposition that will be used will be always even. So, such transposition we call it even transposition. So, then sigma in A n are called even permutations. And obviously, all other permutations are called odd permutations. Okay. So, in particularly S n can be written as A n union a coset of A n. Okay. A n will have all even permutation, that coset will have all odd permutations. Okay. So, now let us try to understand something about the conjugacy of elements of S n. Okay. So, here is the important proportion. So, now using this proportion we can actually determine when two elements of S n are conjugate. So, what is this proportion? This proportion now it actually tells about so what can be conjugate of some given cycle. Okay. So, note that if you are interested in understanding conjugacy of some given sigma, so take sigma from S n. Okay. So, we know that sigma can be written as product of disjoint cycle, write sigma as some sigma 1 etc. sigma of r. So, this is the cyclic decomposition of sigma, let us say. So, then let us say we are interested in some particular conjugate of sigma, let us call it tau sigma tau inverse. Then you can see that this tau sigma tau inverse can be rewritten as follows. So, this is going to be just product of tau sigma 1 tau inverse times tau sigma 2 tau inverse times etc. times tau sigma r tau inverse. So, by multiplying and multiplying by tau and tau inverse in between, you can actually cancel them together and then see that this expression on the left side is exactly equal to tau sigma 1 etc. sigma r tau inverse, which is exactly equal to tau sigma tau inverse. So, now it says that if you want to understand tau sigma tau inverse, it is enough to understand what is this tau sigma 1 tau inverse. Okay. So, indeed that is what we are going to do now. So, we start with some cycle and then see how its conjugate of that cycle looks like. So, take sigma, which is A 1 etc. A k, and this tau inside Sn. So, now we can easily see that if you compute this tau sigma tau inverse, then it exactly look like another k cycle which is given by tau of A1 etc. tau of AK. So, very explicitly if you take the conjugate of the sigma by tau, then this can be written very explicitly as the cycle k cycle tau of A1 etc. tau of AK. So, now once we know this proportion, then it is not hard to state a characterization for conjugacy of elements of Sn. So, let me just write it down. Okay. Before that, we need to write down what is called the cycle type. Okay. Yes, cycle type of sigma of Sn. Okay. So, what is the cycle type? So, you write sigma as some product of disjoint cycles. Okay. This is the cyclic decomposition, and we know that this cyclic decomposition is unique. It is completely determined by sigma. So, in particularly if you take this length of sigma 1, so since all these sigma is they all permute, okay, sorry, they all actually can be rearranged because they all commute with mutually commute with each other. So, you can rearrange them such a way that the length of sigma n sigma 1 is less than or equal to length of sigma 2 less than or equal to etc. less than or equal to length of sigma 4. So, you rearrange them so that the length of the cycles increases. So, then you call the cycle type of sigma to be these numbers, the ordered numbers, length of sigma 1 etc. length of sigma 4. Okay. So, this is called the cycle type of sigma. So, you fix this cyclic decomposition such that the length increases, length of each cycle increases, then the cycles type of sigma is defined to be this length of sigma 1 etc. length of 1. So, note that this is uniquely assigned data to given sigma, okay. That means it is well defined. So, now you call two elements of Sn having same cycle type if the cycle type of sigma is same as cycle type of tau. Okay. So, we say sigma and tau from Sn have same cycle type if the cycle type of sigma is same as the cycle type of tau. So, what is the meaning of this? That means you write sigma as product of disjoint cycles. Okay. The number of 1 cycles appear in sigma, that must be same as number of 1 cycles that appear in tau. Similarly, the number of 2 cycles that appear in sigma must be same as the number of 2 cycles appear in tau, and so on. Okay. Sometimes people use this one shorthand notation. So, they group them together, okay, the number of ones that appears and so on. Then they write this same as 1 power m1, 2 power m2 and so on, some k power mk, where mi denotes the number of cycles, number of k cycles, sorry, I cycles appear in sigma. Okay. So, this notation is also somewhat suggestive, okay, because it's a similar notation used for partition of this m1 plus etc. mk. Okay. So, we will see later that why that partition actually comes. So, it is important to note that because these the length of the cycles corresponds to the orbits, length of the orbits. So, it is very clear, it is clear that if you add all of them, okay, because we have included even trivial cycle, that is cycle having length 1. So, if you add all of them, you can see that you will get exactly the n which is 1 to n, the cardinality of 1 to n. Okay. So, that means, so this is exactly a partition of, so this is exactly a partition of n. Okay. So, now what we want to say, like once you have defined this cycle type, okay. So, this proportion now can be rewritten as follows. Okay. If you take a cycle, k cycle, and then if you conjugate by some tau in Sn, then you get again k cycle. So, that means the cycle types does not change when you do this conjugation for the cycles, and that is exactly going to be true for any sigma, because if you start with sigma, if you write it as product of this disjoint cycles, if you take the conjugate by tau, then you can see that the cycle type of this tau sigma tau inverse is going to be exactly the cycle type of sigma because of this. Now, conversely, we can prove that. So, if you have two permutations sigma and tau having same cycle type, so then we can prove that they must be conjugate. Okay. So, here is the theorem. So, what is the theorem says? So, it gives you characterization for conjugacy in terms of the cycle types. So, two elements of Sn are conjugate, or they are in the same conjugacy class if and only if they have the same cycle type. Okay. So, two elements of Sn, they are conjugate if and only if they have same cycle type. So, one way is proved using this proportion, and we will also prove the converse. Okay. So, we need to first of all verify why this is true. So, then actually we will be done with the proportion. Now, what will be the immediate corollary? The immediate corollary will be, so the number of conjugacy classes, okay, the number of conjugacy classes in Sn is going to be exactly equal to the number of cycle types that we get, which is going to be exactly the number of partitions of n. So, the number of partitions of n is exactly equal to the number of conjugacy classes in Sn, and one knows lot about these partition functions. Okay. And of course, computing them for smaller values are somewhat easy, but one can see that as n grows, then this number of partitions of n also grows exponentially large. Okay. So, computing this for large n will be very difficult. Okay, I will stop here. We will actually continue with the proof of this in the next class. Okay. So, this corollary is immediate from the theorem. Okay. I will stop here.